So we want to welcome everybody again to tonight's webinar. I am Joe Deli Carpini, the Science and Operations Officer, and presenting tonight will be Rodney Chai, one of our meteorologists, and Hayden Frank, one of our lead meteorologists, who helped put this presentation together. So I will hand it off to Rodney, who's going to start off with an overview, and then we'll get into a little more of the information about this historic tornado outbreak. So Rodney, I will pass it on to you.
Well, thank you, Joe, and thank you everyone for joining the first webinar of 2022. Unfortunately, we're going to talk about this devastating, deadly tornado outbreak in parts of the Midwest, and it was overnight December 10 to the early morning hours of December 11, and unfortunately, it was very historic long track tornado, very anomalous supercell type environment. You can see this is the storm reports from the Storm Prediction Center for December 10, and highlighted in red, those are the tornado reports. Blue are the straight line wind reports, and there are also hail reports as well, and they are in green. You can see just kind of two long track tornadoes. The one to the south, that's the tornado that tracked over 150 miles over across 4 states, and then there's also one further to the north as well. Just an incredible outbreak for December. And this is just an overview of the preliminary damage survey results. And this was the surveys conducted by NWS Paducah, Kentucky, and using a combination of like on the ground survey, drones, and airplanes. They were able to confirm this historic long track tornado, and in this case, at that time they were they determined it was at least EF3 damage, with a maximum width of at least 3/4 of a mile. And given the historic event, there were, just expertise, arriving from all over the country. And they conducted this survey over multiple days. So, so this was one of the graphics that they posted on social media. And you can see again, broken down by counties, and how the tornado tracked southwest to northeast across Kentucky. And you can see, it was on the ground for over 2 hours. And the path length over 150 miles, and just numerous injuries and deaths, unfortunately. And this is a reflectivity loop alongside with the tornado warnings highlighted in red, and the yellows are the severe thunderstorm warnings. And you can see just not just one NWS office, but just multiple NWS offices in the vicinity, and it was a very busy night for people, for the forecasters on the warning desk. And I've used the word historic a few times, and just for comparison, so the 1925 tri-state tornado was it tracked, that's 219 miles, and that was back in 1925, and that was a very high-end event. And for comparison, the 2021 long track tornado, it was much longer, and it impacted quite a few populated areas, including the now infamous Mayfield, Kentucky community. And of course there were other communities affected as well, but that was pretty much ground zero for this tornado. So you can see, if it is to be confirmed to be one continuous path, then it would pretty much dwarfed the 1925 tri-state tornado. And this is, taking a closer look at the velocity product from the radar. You can see the classic gate-to-gate. You have the green and the red side by side, and that's pretty much the tornado on the ground. You can see how tight the velocity coupler is, and as it moves north, southwest to the northeast. And again, just a different way of illustrating the. So you have the tornado warning polygons, and then you have those individual tornado reports, and upon the survey, the survey team determined the different levels of EF categories. So, and for comparison, the last, like last year, Southern New England, we did have our tornado outbreak on several occasions, but most of them are EF0 and a couple of EF1s. But in this case, you can see, numerous EF2, 3, and 4 categories. So, when you get to that, when you get above 2, you pretty much you would have pretty devastating damage. So just again, you have that long track tornado to the south, and then further north from Missouri into Illinois, you have another long track tornado. And this is the, one of the derived products that we use. It's called the rotational track. And so where you can see the blue line going from southwest to northeast, that indicates the possible path of the tornado. Now, it doesn't give confirmation, but it can help the survey team to pinpoint exactly where to go, especially in such a large outbreak, any kind of details that can help you to narrow down the places where you need to go to confirm the tornado damage would help. But still spend, like 4 or 5 days just because of the sheer size of the damage. And but this is a product that you can actually, access online. And if you're interested, feel free, during the Q&A session, we can provide you the URL to build this product. And so besides being, historic in the path length, being over 150 miles, just because it is such a powerful storm, and one of the key giveaways is, to what height would the tornado debris lofted into the atmosphere. In this case, on the left-hand side, this 3D illustration shows that the debris were lofted to above 30,000 feet. So basically, when you have a very strong storm, in this case a supercell, you have very strong upward motion in the center of the storm, and so when the tornado hit structures, it would loft this debris very high into the atmosphere. And so the higher the debris can go against gravity, the stronger the storm, and most likely the tornado is very strong as well. So in this case, on the right hand side, you can see this is the reflectivity product, and you can see that that classic supercell signature. But then in addition to that, you can also see the debris spike going away from the center of the supercell. So, and this is something that you don't see very often, but in this case, it's a very historic tornado outbreak, very strong storm, and you'd have debris not only lofted very high into the atmosphere, but also many miles away from the actual storm itself. So it just shows how damaging this system is. So could we see something like this in southern New England? So the answer is yes, we already have, and this was actually the EF3 Springfield tornado in 2011, and some of you might remember that day. So at this point, I'm going to pass it on to Hayden to talk about mesoanalysis and model output.
All right, great. Thank you very much, Rodney. We are going to look at some of the guidance that forecasters really utilize. We utilize this for winter weather quite a bit now too, but particularly for thunderstorm and assessing severe weather threat. And you've probably heard us mention, if you've been on these presentations before, the HREF model. It's basically an ensemble of several different models that really handle thunderstorm and severe weather forecasting quite well. And this really has helped us out. So one of the things you'll notice, we're looking at what we say 500 millibars. That's roughly 18,000 feet above the ground. And where you see the triangles, that's actually indicating a 50-knot winds. And then you know how those each line represents an additional 10 knots. So we're looking at about 70, 80, 85, 90 knot winds with this upper level energy. That's what we refer to it. So it was really quite impressive. Kind of jumped ahead there. But yeah, so you could really see the atmosphere. This is something you'd see in the wintertime. You don't see this usually when we're talking about thunderstorms. But this is why this event became historic, as Rodney referred to it. And we'll talk about that in a bit. So moving a little down in the atmosphere, we're looking at 700 millibars. Again, so we're roughly about 10,000 feet. And give you some reference where here's, you know, the focus for the big severe weather into Kentucky there. And you can see we've got over 60 to 70 plus knots of wind in that layer. That is really impressive. And you're also in the right rear quad of that strong wind profile in the upper jet, and that can be very conducive for severe weather as well. Again, it's so unusual to have winds in the 500 millibar to 700 millibar layer in that 10 to 20,000 foot range in the atmosphere of say 60 to 90 knots in a severe weather event. You usually see that when we're dealing with a winter storm. So the atmosphere was extremely, as we refer to it, anomalous, quite unusual for December, considering we were preparing for severe weather in this part of the country. So we look down one more layer around 850 millibars. Now we're about 5,000 feet. Again, we're getting, you know, winds in this layer of 50 to 60 knots. So extreme, what we call dynamics in the atmosphere, which means, and we're going to talk about this in a bit, you don't need as much instability because you have such power in the atmosphere. Those winds, that's your forcing for the thunderstorms. You don't need as much instability, and we're going to talk about that more in a bit here, that you would say if this were May or June. And then looking at the surface, what you'll notice is a fairly strong surface low. You know, it's basically going sub 990 millibars, tracking up through the Great Lakes. That's usually not a good recipe in December. And in the yellow and orange coloring into the Tennessee Valley, you can see those are surface temperatures. And keep in mind, this is late in the evening, so you have temperatures, you know, well into the 60s and into the 70s during the evening in mid-December. You've got powerful winds aloft that we were looking at, and you have all this moisture streaming northward from the Gulf of Mexico. And that's never a good recipe. So putting this all together, just looking at the HREF model and I want to summarize this all. We had extremely strong winds aloft, so the atmosphere was very dynamic. We had unusual warmth and moisture streaming north of the Gulf of Mexico. You could see temperatures in the 60s and 70s, and that's an evening forecast. And then you had a cold front approaching from the west. So you have all the dynamics. Now what about the instability? And that's what you need to generate the severe weather, which we're going to look at on the next slide here. So this may look a little complex, but let me kind of go into it here. This is looking at 2.5 to 5 kilometer, what we call updraft helicity. Basically, it's a way of saying there's spin in the mid and upper part of the atmosphere. Studies have shown that's very conducive for severe weather. And where you see the yellow and reds, those lines, that is where the computer model, the HREF model ensemble, is forecasting the greatest spin. Now, it's a model. It's not going to be perfect, but it's going to get you in the ballpark normally. And those little blue dots, the red dots, the blue dots are noting severe weather report. The red dots are actually noting where there were confirmed tornadoes. And notice the clustering. Again, all your severe weather reports are in that southwest to northeast orientation. And notice how they're clustered right where you see the bulk of those updraft helicity swaths. Okay, you can really see, and then as you get further out into, Illinois, you still see some in northern Illinois, but they start to diminish, and you could see them really clustering into the Kentucky, the Tennessee area, northeast Arkansas, and sure enough, that was where the most reports of severe weather happened, unfortunately. So this really can help a forecaster gauge what is the potential with a particular event. Okay, so this is another example of a parameter we look at. It's called the significant tornado parameter. And again, what it's looking at the amount of instability in the atmosphere along with the winds aloft. The stronger the winds aloft are, combined with the greater the instability is, you're going to see a higher number here. Again, so if you have more winds and less instability, you can make up for this with stronger winds, or vice versa. If you have less winds, you can make up with it with the instability. And then it's incorporating that turning in the wind in, say, the lowest 5,000 feet of the atmosphere. So again, you can see remarkably well how this tool performed. Notice where your highest significant tornado parameter was forecast, right in the area from southeast Missouri through Kentucky into southern Indiana, and that's not a coincidence. And then you actually see, stripes of severe weather out into Illinois, and you can see actually where it extended a little bit 5% prob. You can see where there was some enhancement there. So this tool did remarkably well. It's not perfect. You'll see severe weather reports outside of it occasionally, but what it does, it's going to give the forecaster the confidence and us to zone in on the area that's most likely to be impacted and the area that not only impacted, but impacted significantly. And unfortunately, this was historic and tragic, as Rodney showed with the pictures, and we heard from the news reports over the few days following the tornadoes. Okay, so now what we're doing is we're real time. Let's say we're in the office. You're going to have a couple forecasters issuing the warnings, but it's also important to have what we call someone keeping those warning forecasters situationally aware, because the atmosphere can change within 15, 20 minutes, even quicker. So you have someone dedicated to looking at the real-time analysis, and this is what we tend to do in the office. So the first parameter we are looking at is surface-based CAPE. Okay, we've got 1,000 to 2,000 joules per kilogram of surface-based CAPE working up into the southwest Kentucky, southern Illinois. This is just before that tornado is going to approach the Mayfield area, that long track tornado. So again, instability of these values for this particular part of the country, well, it's unusual in December. They can often have the instability much higher, say in May, June. But what is different is you don't have 60, 70, 80, 90 knots of wind in that 10 to 20,000 foot portion of the atmosphere. And when you combine, we call wintertime dynamics, wintertime jet dynamics, with spring and summertime instability, these type of events unfortunately occur. So one of the tools we've been utilizing, when I got into the Weather Service and when Joe got into the Weather Service, we were, one of the big parameters was the surface-based CAPE, what we just looked at. Over the last, I'd say 4 or 5 years particularly, it's more been focused on where is the CAPE located. And that is actually shown to be more important than the overall CAPE. And this is something called the 0 to 3 kilometer CAPE, the low CAPE in the atmosphere. There are correlations, in fact, significant correlations, that when you have CAPE values in that layer over 75, especially over 100 joules per kilogram, those are very favorable for not only severe weather, but tornadoes. And notice these values, 75 to 100 to 125 joules per kilogram. We see that in a lot of our tornadoes that we get in southern New England. Sometimes we don't have much surface instability, but the low CAPE, that important CAPE as we call it, the 0 to 3 kilometer CAPE, can be relatively high. So it's not only the amount of instability in the atmosphere, but it's where it's located. And for tornadoes in particular, we're tending to look down low because that's where your spin is. That's where the winds are changing direction with height the quickest. Okay, another big player in severe weather are mid-level lapse rates. And when we call mid-level lapse rates, we're looking for the temperature change roughly in the 700 to 500 millibar layer, so in that 10,000 to 20,000 foot range. The quicker the temperature drops in that level with height, the greater your mid-level lapse rates are. One of the reasons in southern New England we often don't get the severe weather that they get out in the Midwest is because our mid-level lapse rates are usually what we see in those blue dots there, around 5.5. When we tend to get our big severe weather outbreaks in New England, such as June 1st, 2011 tornado outbreak, we're tending to look at mid-level lapse rates, 6.5 to 7 to even over 7.5. And that's what was in place across the Kentucky area, Northeast Arkansas, Southwest Missouri. So again, it wasn't a coincidence why this happened, where it happened. There's a number of parameters that came into place. It's like building a cake. If all those ingredients are in place, then you could be in trouble. So one of the more important factors is looking at the winds in the lowest layer of the atmosphere, in that 0 to 1 kilometer layer. It's called storm relative helicity. It's measuring the spin. And basically what that's saying is how quickly the winds not only change speed, but especially direction as you go up in the atmosphere. One of our parameters that we start to get concerned about tornadoes in our area is over 100 units. Well, look at what the values were in place across Kentucky, Tennessee. We're looking at over 300, over 400 units of 0 to 1 kilometer helicity. So not only do we have the strong winds aloft, we've got the 0 to 3 kilometer CAPE, we've got the steep mid-level lapse rates, and we have extreme low-level helicity. That is a recipe for disaster, unfortunately. And, these parameters, the significant tornado parameter, the values for this particular event, generally in the 4, 5 to 6 range, and that is incorporating, say, the instability, the wind fields, the winds turning with height, all those things put together. When you start to see values of 1 or 2, you get concerned. Even the values could be even under that. Give you an idea, can we get this here? Rodney was saying, can we get this here? Of course. Fortunately, it's at a much, much lower frequency. But to June 1st, 2011, we had significant tornado parameter 3/4 If you go back to the June 9th, 1953 Worcester outbreak, that had a very similar atmosphere. So these conditions can happen in New England. Fortunately for us, they're quite rare, but the atmosphere doesn't care what part of the country it is. If the parameters are there, you can get a plains-like outbreak in the Northeast, and it does happen on occasion. So looking at the soundings again here, we talked about where you're looking at those 700 to 500 mid-level lapse rates. You can see that dramatic change with height in that layer. So that's giving you the steep mid-level lapse rates. You also know below that there's initially like a cap in there, and that's like a warm layer that kind of keeps convection somewhat thunderstorms suppressed until you warm enough, and then all of a sudden you get explosive development. What that also allows you to do is to keep from getting too many thunderstorms around, because remember, these thunderstorms are competing with each other. And you'll notice in the radar loop that Rodney showed of those big tornadoes, that long EF4 track, there was nothing to the south. That inflow going into the thunderstorm, you had all that warmth, humidity, and moisture, nothing to interrupt it. If you had thunderstorms just south of there, you probably would have still had tornadoes, but they would have been weaker and short-lived, because there's only so much atmosphere that the thunderstorms can compete with. So if you have too many of them, you tend to get shorter-lived, weaker tornadoes. But unfortunately, this had everything. Tremendous turning in the atmosphere. The values and the soundings were just pretty incredible for this event. And with that, I am going to turn it back to Rodney, who's going to talk about the messaging and how this information was conveyed both to emergency managers, to the general public. So with that, Rodney, you ready to go?
Yes, Hayden, thank you. All right. So this is the SPC outlook that a lot of you would probably be familiar with. And, when you take a look at this, I mean, it's just like, you think this is in the middle of convection season, but no, it is mid-December, and going from the top left, and then as we advance eventually to the bottom right, you can see how SPC, increasingly increased the severity of the outlook, and eventually they had a moderate severe risk. And pretty much, SPC was on point. I mean, with highlighting where where we could get the most coverage of severe thunderstorms was actually right in the moderate and even parts of the enhanced risk area. And this is the SPC Day 1 outlook overlaid with the preliminary reports, and you can see again. SPC did a great job forecasting the severe outlook, and this is taking a look at the tornado probability, which plays a big role in the outlook that we saw just now. And you can see the moderate risk area is almost co-located with the 15% tornado probability, and the enhanced risk was the 10% tornado probability. And unsurprisingly, most of the tornado reports were in the 10% and 15% area. And taking a closer look at a zoomed-in version of the region, you can see clearly the moderate risk area straddling different different states, including Arkansas, Tennessee, into Kentucky, and parts of Illinois and Indiana as well. And Maysville was not shown. It's not shown on this map, but it's actually in the moderate risk area. And then on the right hand side, there was the tornado watch that was issued that night. And and notice the wording. So several strong tornadoes are likely. And that's pretty strong wording for tornado watch. And then towards the bottom, you can see not only do you have a high likelihood of tornadoes, you have a high likelihood of EF2 plus tornadoes alongside with severe winds. So again, a very conducive environment for long track damaging tornadoes. And so on the left hand side, you see what we call an MCD issued by the SPC. That's the mesoscale discussion. So so the previous two slides, those were the outlooks or the forecasts, but the SPC will issue mesoscale discussion from time to time as an event unfolds, and it is to sometimes to hit home the point that this could be a highly anomalous event. And indeed, notice the wording again: strong to potentially violent tornado, ongoing and expected to continue. So basically, people, communities in the path at that point, basically you just have to go to shelter. And then on the right hand side, that's the mesoscale discussion that they discussed. So again, the red are the tornado warning polygons, and in this case, the green are the reports. And again, you can see just you can almost kind of trace out the path of the long track tornado with when you overlay all the polygons together. So again, you have one from northeast Arkansas all the way into Kentucky, and then further north you have the from Missouri into to Illinois. And I believe you also overlaid the warnings from a separate event, again high-end event. SPC also issued a moderate severe risk, but there was further north, and which actually made it even more anomalous, because you can kind of argue that further south, even in December, you can have a severe outbreak, but mid-December, talking about the northern Great Plains from Omaha into just north of Des Moines, even to parts of Minnesota, that's really unheard of. And I believe Minnesota had their first tornadoes in December, so that's again very highly anomalous event, but thankfully much fewer fatalities than the event that we are talking about today. So we have all the warnings, and a lot of people use the NOAA weather radio, and we receive the weather alerts on the phone. But in order to build a weather ready nation, social media has also become a very important way for us to convey our messages. And notice how great a job NWS Paducah did in conveying the severity of the situation to their followers. And of course, the tweets cannot replace the actual warning, but for people who spend a lot of time on Twitter, on Facebook, social media is a great platform to reach out to your communities. So in this case, on the left-hand side, they, again, they included like a radar still image with, and then highlighting the area of the greatest tornado threat. And notice that Mayfield is actually right in the center of that the circle. And then they did a quick forecast. They described the, basically what I would say the 5 Ws. So you have the what time, what location, what threat to expect, and so again, strong long track tornadoes possible. And then on the right hand side, you can see, with the timestamp right before 9 p.m. Basically, they were saying, okay, there's strong likelihood of a tornado forming imminently, and the path that it is likely going to take. So if you are in all these communities, be sure to take shelter And that was even before the tornado warning was issued. And for those of you who have been under a tornado warning, your phone would would buzz with the alert, and the tornado siren should also be sounding, so that it's the time to go to your warning shelter. But again, you cannot overemphasize the importance of social media in this case, because it does give people a heads up, that be prepared. You will probably be using your tornado shelter later that night. So, and then as we progress through the night, you can see the increasing severity of the tone. And then by just after 10 p.m., they say if you live in or near Mayfield, you need to be underground if at all possible. Get to the shelter now. And so that was the actual tornado warning that was issued, for including Mayfield, and they did emphasize this damaging tornado is likely, and with the tennis ball size hail possible, and this is a life-threatening situation. People need to take shelter. And then as the severity of the situation became apparent, and usually, the officers use tornado emergency sparingly. So basically, it is one way to think about it is if a tornado is confirmed and is causing a lot of damage and it's about to impact a populated area, the warning meteorologist could opt to use a tornado emergency, and in this case, it was a life-threatening situation, and there's just no other way to describe it. It's you would likely be killed if you don't go to the shelter. So concluding thoughts. We asked ourselves, was the messaging effective, and how do you plan for an event like this? So it's hard to look at pictures like the one in the bottom, but objectively speaking, the event was well forecasted as shown by the SPC outlooks. The threat was clearly messaged, not only through the traditional warnings, but also through social media. But ultimately, it was the greatest loss of lives since 2011 from a tornado outbreak, and there were some mitigating reasons for that. Number one, it was a nocturnal outbreak, so some people are sleeping. They might not be at their phone. So research has shown that tornadoes at night are known to be 2.5 times more likely to be fatal during the day. And secondly, quite a number of fatalities occurred in the Amazon warehouse in Illinois, as well as the candle factory in Mayfield, Kentucky. So you have in this case, you bring the complication of a commercial setting. If you're at home, you know where to go. Unfortunately, multiple reports and interviews did indicate that the workers and the warehouse and the candle factory did not know where to go at that time. So that played a role in the fatalities. And I would leave you with this quote from this social science researcher with the National Severe Storms Lab. When people go to work or to a business, it is situational vulnerability, i.e. the situation you find yourself in when a tornado occurs. So, and then the final point is, do you have a way to receive severe weather information at night? And with that, I will pass it back to Joe.
Okay, thanks, Rodney, and thanks, Hayden. And I'll leave that up as we go through some questions here. So let's see, we're going to start with a question from John. How long and for what distance was the June 1st, 2011 EF3 tornado on the ground? Hayden, I'm going to try and remember that. Maybe you can help me. It was from Westfield over to Southbridge, I believe.
It was approximately 40 miles. If I remember correctly, somewhere in that range. I think that was it might have been 38, 39. I can't remember the
Yeah,
exact
I think it
number.
was 39 now that you mentioned it. And I think it was on the ground, what was it, from just before, I think it was just after 4 o'clock until about 5:30, 5:40. So about an hour and a half, roughly.
Yeah, and that
Yeah.
exactly. Yeah, I think it crossed, yeah, over when it was in Berkshire County, in that area, it was producing, I think that's where they had the really, really big hail. And then yeah, right, Westfield was the
Yeah.
first touchdown of it.
All right. Good question. One from Mike and Hayden. This is probably more for you. Does local topography play any role in the 0 to 3 kilometer helicity, or does the topography help to enhance or diminish an existing tornado? Good question.
Yeah, very good question. And you know, we feel that it does play a role. Um, there is some evidence if you look at tornado climatology, even in the Northeast, that there tends to be some enhancement right in that Connecticut Valley area, because you tend to have the winds, when we say surface winds, back a little more to the south southeast. So that increases your low level helicity. That what we talked about, that 0 to 1 kilometer helicity. How much of a role it plays, it's really hard to measure. We do think it plays a role. And you obviously can have the other situation where, the way topography is can cause weakening too. Although if you have a, big tornado, it's not gonna, if it's going over a little, hill or even a decent sized mountain, it may not, cause it to fall apart or anything like that. But topography does play a role. It's hard to measure the exact role it plays. There's so many contributing factors.
Okay, and here's another tornado question. Hayden, you're probably the expert to answer this one. You heard that the long track tornado, the rear flank downdraft, was held at bay. Otherwise, the funnel would have lifted sooner. So, you want to talk a little bit about that?
Yeah, so basically what happens is you have the rear flank downdraft, that if you picture a tornado, if you're to the south of it, that the rear flank downdraft wraps around it. And then on the east, or you say if you're to the south of it, the right side of the tornado, that's where your inflow is. So if you're doing, storm chasing, and the winds at your face, that's usually a sign that the tornado is going to fall apart, because you have that cool outflow. But if the wind's at your back and you're to the south of it, that's that warm inflow going into the tornado. So that rear flank downdraft can help to spin the rotation up, but everything has to be timed perfectly, for a tornado to maintain itself. That's why you need relatively strong winds in the atmosphere. Otherwise, the kind of rear flank downdraft ends up kind of catching up to the storm and killing it, because you get the cold air wrapping into it too much. So it's a balancing mechanism.
All right, and here's a question about the warning from Landon. Given that the storm was forecast to affect Mayfield with 30 to 60 minutes of lead time on Twitter, the ones that Rodney showed, why was an official warning not issued at that time? It's a good question. We'd have to get in the head of the staff that night. But Hayden, do you have any guesses on that?
Yeah. So what time was the official warning go out? Like how much lead time was it exact? What was it?
I
Half
thought
hour?
I thought it was over a half hour. It
Yeah,
wasn't quite
I thought
60 minutes, but
I thought it was too. Again, we're not, social scientists. What I've heard social scientists though that study these things saying with tornadoes there sometimes can be too much lead time. Obviously that's not in all cases, but there have been some social scientists that have studied that after, say, people are sheltering in place for too long, they become restless. Again, that's kind of out of, um, you know, our field of expertise, but I've heard that used. Obviously, we try to provide as much lead time as we can. I'm not sure, how what they were thinking. I know, I mean, all forecast offices did an excellent job in getting the warnings out. I know that there was a tremendous amount of lead time. I mean, you can only give so much because even these big tornadoes, they tend to fall apart, after a certain period of time. It's extremely, extremely unusual to have a tornado track this long. I think it was, I think 160 miles, somewhere in that range. 127 completely on the ground was confirmed, something in that ballpark, which is extremely, extremely unusual. And also the other issue too is that they tend to have what we call deviant motion at times. So it's hard to provide like over 45 minutes of lead time because it's impossible to really gauge the exact direction. It could shift 3 miles south or 4 miles north. That's the dilemma for warning forecasters.
All right. Yeah, I've heard that too about the being too much lead time. So, because then people will kind of be complacent or go run out to get something done before the tornado actually comes. So, yeah, but we'd have to kind of get in the head of the staff that night, everything else that was going on. A few more questions, and then we'll get to our storm briefing. So from William, he says, I know that tornadoes happen in other places around the world, but does any place else see the number, severity, and occurrences that we now see year after year? Rodney, why don't you touch on that one?
Yeah, thanks for the question. So, you're right that tornadoes do occur worldwide. They can really occur anywhere. But I would say that the United States does lead the world in the number of tornadoes and also severity. Just because when you have so many tornadoes, it's from a statistical standpoint, some of them are going to be very severe and devastating, like this one. And the reason for that is because the U.S., especially continental U.S., we have a very unique geography. I mean, and typically you get severe weather outbreak and consequently tornado outbreak from a clash of air mass. So we have the Gulf of Mexico, which is to the south, which is a great source of moisture and warmth. And if you look closely in the center part of the country, it is pretty flat. Although I've lived in Kansas State, it is not exactly flat, but it is mostly flat. So you have the cold Canadian air, that rushes south, that meets up with this moist air from Gulf of Mexico, and it creates an environment where, especially in the spring and fall, when you have a clash of air mass like this, you just have a very conducive environment for severe weather and again consequently tornadoes. So so the U.S. So while tornadoes are not exclusive for the U.S., but the U.S. does lead the world in the number of tornadoes and severity.
All right. Thanks, Rodney. And a few more questions here. A bunch of them, I knew we were going to have this question, guys. Is it related to climate change, or does climate change make events like this more likely to occur? The jury is kind of out regarding climate change versus tornadoes. There are research is being done, but they haven't come to any conclusions. But I think you can say, that does make events like this more likely to occur. I think you can say yes. Warming, more moisture, stronger winds aloft. The ingredients that Hayden showed have been tied to that. So the likelihood is higher, but can you say there's an exact number of tornadoes is more? No, not yet. So that's something that's being studied by the climatology people. So, I think maybe after a few years, worth of study and data, we might start to see some initial conclusions on that. So I think that is it. If I didn't get to your question in particular, you can always email me and we can get the answer to you. I know we have a bunch in there, but we want to also get the weather briefing in here because I know I heard we had some snow on the way, guys. So I think we probably want to talk a little bit about that. So
you were working it today, so
yeah, and I was lucky to work today, so I think I will take the lead on this. But Rodney and Hayden, feel free to chime in. So one of the first things I wanted to do was just before even the storm was on the horizon, we were going to talk a little bit about kind of the big picture of what's going on. And I just want to start off with a few slides on that. So as you probably know, we're in a La Nina pattern this winter. And, for those who may not be familiar, it's the cooling